Power series. You guys have all encountered power series in the past, I'm sure. So this is just going to be a quick application of everything we have learned about series applied to this very special class of functions called power series. Okay. So by definition, given a sequence of reals Cn, the series summation Cn x raised to n is called a power series. Okay, so Cn, the power series is parameterized by a sequence of reals Cn. Now, typically, a power series, the summation starts from 0. That's just convention. It just becomes. So the convention is to start from 0 to infinity rather than 1 to infinity, right? Of course, none of that changes anything meaningfully. So this summation from 0 to infinity Cn x raised to n, which is a series of real numbers for every x, is called a power series, right? This is in particular, you should interpret this as a function of x, right? Because for the Cn is of course a given sequence of reals. So if you fix any real value x, then summation 0 to infinity Cn x raised to n is a series, right, of the kind that we have been studying so far. It may converge, it may diverge, and so on. So that function of x, right, is called the power series, right? What does that mean? That when this series converges, then we interpret this function to take the value associated with the limit, right? So this function will have its domain. The domain of this is going to be the set of x such that the series converges, right? So this defines a function. That function is exactly what we call the power series. The domain of the function, I hope is clear, is basically the set of all those real valued x such that for that particular x, the series summation Cn x raised to n converges. Okay, so this is what is a power series. We will have a lot more to say about this series going forward. So when we study continuity and differentiability and stuff like that, we will have a lot more to say about power series later. But at this point, what we are going to do is, using the machinery for series that we have built so far, what we are going to instead study is just the domain of the power series, right? So what is the structure of the domain of a power series? That is what we are going to study right now. Okay, and in fact the domain of the power series is given by the following theorem. So given a power series summation 0 to infinity Cn x raised to n, let alpha be defined as follows. It's the lim sup of absolute value of Cn raised to 1 by n. Okay, now let us define R to be 1 by alpha, right? Now remember, alpha is the lim sup of a certain non-negative sequence. So alpha can be 0, alpha can be a positive real, or alpha can be infinity, right? So when I say R is 1 by alpha, well, these standard interpretations apply, that if alpha is 0, take R to be plus infinity, and if alpha is infinity, take R to be 0. Okay, so with these interpretations, the final statement of the theorem is that the power series converges when absolute value of x is less than R, and diverges for absolute value of x greater than R. Okay, that's the statement of this theorem. So this R is in fact referred to as the radius of convergence. Right, so this theorem essentially tells you what is the domain of any arbitrary power series, right? If you give me any power series, summation Cn x raised to n, associated with that power series is a number r. R could be anything, it could be a non-negative real or it could be plus infinity. Okay, this value r is what we call the radius of convergence of the power series, and in this the interpretation of this is that it determines the domain of the power series. Okay, in particular the domain of the power series is those real values which have an absolute value less than r, and specifically if you take any x whose absolute value is more than r, then you are guaranteed that the power series will diverge. Now, it's strictly not completely specifying the domain, so I stand corrected to some extent, because in particular, if you take x to be either plus r or minus r, which is kind of at the boundary, right, of the radius of convergence, this theorem doesn't tell me whether the series converges at those 2 points or not. So in particular, it doesn't tell me, it doesn't confirm conclusively whether or not x equals plus minus r lie in the domain of the power series, but it almost specifies the domain. Namely, that absolute value of x less than r belongs to the domain, and absolute value of x greater than r in fact does not belong to the domain because the series under consideration diverges. Okay, so this is what we have to say about the domain of a power series. Okay, and how do I get the radius of convergence? You first you look at the coefficients of the power series. So these CNs are typically called the coefficients, right? You look at the coefficient sequence and define alpha to be the lim sup of absolute value of Cn raised to 1 by n, right? And R, the radius of convergence, is simply the reciprocal of this alpha. Okay, so that's how you obtain the radius of convergence. And now we have said, well, for what values of x does the power series converge? For what values of x is it guaranteed to diverge? And as I said, the only ambiguity that is left at this point is whether or not the power series converges at plus minus r. Okay, now I actually don't need to do the proof of this. The proof of this, if yeah, maybe I'll leave it as a complete exercise to you, is essentially a trivial application of the root test. Okay, essentially all you have to do is show that if mod x is less than this value of r, then in fact summation Cn x raised to n converges, and in fact converges absolutely. If mod x is greater than r, prove that summation Cn x raised to n diverges. Both of these statements will in fact follow from an application of the root test. So since we have already covered the root test, this particular statement about power series is in fact a trivial consequence. Okay, so I leave it for you to actually go through with this step. You have to make sure that you understand the corner cases well, right? Alpha equals 0, alpha equals infinity, but again, I'm going to leave that as an exercise to you. And what I'm going to do is conclude by going through a few examples of power series. Okay, so let's do a few. So suppose you look at something like summation n raised to n x raised to n. Okay, in this case Cn is n raised to n, in which case you can also check that alpha is in fact equal to infinity, which will imply that r is actually equal to 0. The fact that r is 0 implies that, well, for no non-zero value of x does this series actually converge. In this particular case, the coefficients grow so fast that for any non-zero value, for x is equal to 0, of course, any power series converges for x is equal to 0, right? But for no non-zero value of x does this series converge. And that is in fact indicated by the fact that its radius of convergence is 0. Okay, now let's look at more benign series of the form n times x raised to n. Okay, in this case your Cn is just n. Check for yourself that alpha in this case will end up being 1, and so the radius of convergence is also going to be equal to 1. So when you look at the power series, again 0 to infinity is implicit in all of these. When you look at the power series summation n x raised to n, in fact it converges for mod x less than 1, diverges for mod x greater than 1. Okay. Final example, let's look at the power series x raised to n by n factorial. Okay, so in this case your Cn is equal to 1 by n factorial, right? And now you have to ask yourself, what is the alpha, right? It turns out in this case that alpha is in fact 0, which implies that the radius of convergence is infinity. Okay, again I leave it for you to show why that's the case, right? It boils down to actually something similar to what we have talked about before, which is that if you look at the nth root of n factorial, that tends to infinity, which implies that alpha tends to 0. Okay, but again I leave that formal justification to you. In this case r is infinity. What does that mean? That this this series actually converges for every real valued x, right? And in particular, this is a very important series. This is in fact the definition of e raised to x. Okay, in particular, if you choose x is equal to 1, you will see that that is in fact that is in fact exactly how we define e to be. Well, that this series is in fact e raised to x, namely that the value of this series is the same as the value of the limit of the series when you put x equal to 1 raised to, well, x, that all that will come later, right? So we will give a formal justification of this later, but at this point I'm just giving you this as an input, that this series which converges for every real valued x is in fact the definition of e raised to x. So we will have more to say about this later. Okay, so that concludes all I wanted to cover with respect to power series. At this point, all we know is that if from our understanding of series, associated with every power series is a radius of convergence, and we have talked about how it is that one computes this value, and the radius of convergence r satisfies the property that the power series converges for mod x less than r, diverges for mod x greater than r. Right, that is all we have said about power series so far. We will have a lot more to say about the continuity, differentiability properties and so on, and the integration properties of power series in later chapters of this course. Okay, but this is all for now.